This is the video for section 1.7 notes, slides 38 through 41. So in section 1.7, we are talking about something that we refer to as rate of change. So initially, we're going to be talking about something called the average rate of change. So the average rate of change is the amount of change between two particular points divided by the time that it takes. Now, this is really not a new idea. This is actually just the idea that we know to be slope. Now, slope, we have a couple different ways of referring to this, right? Sometimes we call it M. We use the letter M to talk about slope. We talk about, we might write it like this using a symbol for triangle that represents change. So we might call it like change in Y divided by change in X. We might talk about it like that. We might remember the slope formula, which we, might say like y2 minus y1 over x2 minus x1. So all of these different things are kind of interchangeable, but all of them mean the average rate of change of a function over a particular domain. Now, average rate of change we are also going to refer to as the slope of the secant line. Now, a secant line, you may recall from geometry, if we had a circle and we drew a line that intersected the circle twice, we would refer to that as a secant. And going right off of that, we also might remember if we drew a line and it intersected the circle once, we would refer to that as a tangent line. So we'll be getting into that a little bit later. All right, so it says, question number 1 just says, find the average rate of change of f, which is square root of x plus 4, on the domain 5 to 21. So what does that mean? Well, that means we want to know the slope of this function from x equals 5 to x equals 21. Now, if we think about the graph, what is the graph of f of x equals x plus 4? That is the square root function that has been shifted 4 units. Which way, left or right? Well, remember, if it's plus 4, it's counterintuitive, and so it would be to the left 4, right? Because if you plug in 0 there, you get 0 plus 4, square root of 4 is 2, and so you get 0, 2 right there. Or if you plug in negative 4, you get square root of negative 4 plus 4, that's 0, so you get negative 4 comma 0, right? All right, so now we want the average rate of change, or the slope, from 5 to 21. All right, so x equals 5 is right here. X equals 21 is somewhere over there. So 5 to 21. So we are calculating, and let me change the color so we can see it. We are calculating the slope of this secant line. All right, but very simply, we are taking the y value at 21. So that we'll call that f of 21 minus f of 5. That's like y2 minus y1 over x2, so 21, minus 5, right? So very simple. This is the slope, or the average rate of change of this function on the interval 5 to 21. All right, so f of 21, so of course, square root of 21 plus 4, minus the square root of 5 plus 4, all divided by 21 minus 5. All right, so 21 plus 4 is 25, square root of 25 is 5, minus 5 plus 4 is 9, square root of 9 is 3 over 16. So I get 5 minus 3, 2 over 16, which is 1/8. So now look at this picture, all right? We are going from 5 to 21, we're going on a positively sloped line, so positive 1/8, of course, and not very steep at all, right? So up 1 and to the right 8. So this seems to be about right. All right. So that is very simple, average rate of change. In general, we might write it like this, m, and then we write subsecant, so slope of the secant equals f of b minus f of a over b minus a. And this is to find the average rate of change of f on the interval a to b. All right, so that is average rate of change. All right, now, what we're going to do is we're going to talk about the average rate of change on this function over a number of different intervals. All right, so for instance, starting off, it says sketch the graph of f of x equals 2x squared on 0 to 5. All right, so 0 to 5. All right, so let's start with 0, of course. 2 times 0 squared is 0. All right, and let's just pick 1. 2 times 1 squared is 2. So notice the labels here. So this would be about 0, 2. All right, let's go to 2. 2 times 2 squared. So 2 times 4 is 8. So go to 2, 8, about there. All right, let's go to 3. 2 times 3 squared. 2 times 9 is 18. So I'm going to go up to 18 here. And then let's go to 4. 2 times 4 squared. 2 times 16 is 32. So I'm going to go to about there. And then lastly, let's go to 5. 2 times 5 squared. So 2 times 25 is 50. So I'm going to go here. All right. And so we're basically just graphing the right half of this parabola. I mean, it would be the full parabola, but we only want to view this part. All right. So anyway, it says find the average rate of change over the interval 2 to 4, over the interval 2 to 3, over the interval 2 to 2.5, and over the interval 2 to 2.01. All right, so let's first start off. Okay, I'll use, let's say I'll use this color. All right, so 2 to 2.4. All right, so here's 2, 2 to 4. All right, and here's 4, right? So we are finding the slope of this line. All right, so 2 to 4, I'm going to draw this line in as best I can. All right, so we get that line. All right, so now 2 to 4. So we are taking y2 minus y1 over x2 minus x1. So slope would be, all right, so it'd be 32 minus 8 over 4 minus 2. So 32 minus 8, 24 over 4 minus 2, 2, which means we have a slope of 12. All right. So that should be easy enough. That is not calculus, right? It's just some basic algebra. All right, 2 to 3. All right, so now I'm going to change the color again. All right, so 2 to 3. So now we're connecting these 2 points. All right, and so now I'm using different colors so that we can recognize that this slope should be slightly less. Now, I know my drawing is not great, but you should be able to see that the slope connecting 2 and 3 is going to be less, slightly less than the slope connecting 2 and 4. All right, so let's do the calculation. All right, so m equals, all right, what is the y value at 3? That is 18 minus the y value at 2, which is 8, divided by 3 minus 2. All right, so I get 18 minus 8, 10 over 1. So we get a slope of 10. Now, what did we say? That the slope of the line connecting 2 and 3 is slightly less than the slope connecting 2 and 4, which is true. All right, so now let's go from 2 to 2.5. All right, so now this is going to take just a little bit more kind of brain power, not a huge deal. All right, 2.5. We did not already figure out that point, but if I draw in this secant line, you can see that the slope should be slightly less than the previous one. So slightly less than 10, I suppose. All right, so 2 to 2.5. Now, for our purposes, 2.5, I'm going to rewrite it as 5 halves. All right, so what is the y value at 2.5? Well, it's going to be 2 times 5 halves squared, right? 2x squared, remember, is our function. So 2 times 5 halves squared minus 8 divided by 2.5, or 5 halves, minus 2. All right, so now just a little bit of extra work here. 2 times 5 halves squared. What is 5 halves squared? Well, that would be 25 fourths. So 25 fourths times 2 is 25 halves minus 8. Well, 8 would be 16 halves over 2.5 minus 2. That's 1 half. All right, 25 halves minus 16 halves. 25 minus 16 is 9. So we have 9 halves divided by 1 half. Well, 9 halves divided by 1 half, that would be like multiplying by 2. So this slope equals 9. So what did we say once again? That this new slope would be, once again, slightly less than the last one, which it is. All right, and so the last one we're going to do, and this calculation is, I guess, a little bit more annoying, but from 2 to 2.01. Now, where is 2.01? Here is 2. Where's 2.01? It's so close to the number 2 that it's indistinguishable, right? But if you were to connect those two points, you would get a slope, once again, that is slightly less, well, than 9 now, right? Okay, and so the calculation is kind of annoying, I suppose, but we get 2 times 2.01 squared minus 8 over 2.01 minus 2. All right, and so now 2.01, kind of annoying, right? What is that? Well, it's actually, like, you could rewrite it as a fraction, all right, which is annoying. But basically, if we do this calculation, we get about 8.02, I believe. All right, now, if we do that, we see it's slightly less than 9. So now, let's think about what's going to happen as I get even closer, like 2 to 2.01, 2 to 2.001, 2 to 2.000000001, right? What's going to happen? This number is going to get smaller and smaller and smaller and smaller. But to what end? At what point does it stop? So that's what's going to bring up our next idea. All right, on to slide number 40. So what are we really finding as that number gets even closer to 2? All right, so what are we really finding? We're actually finding, and let me change colors again, the slope of the tangent line. Now, this is really important, okay? What was the tangent line once again? Remember, on a circle, that was the line that actually only intersects the circle once. So if I go back here, if we have these 2 points and they get infinitely close together, then they're actually not 2 separate points. They're actually 1 point. And so the line that we would be drawing would actually only intersect the curve once, and then it would be called a tangent line. So we're finding what we call the slope of the tangent line. But another way we refer to it is actually, well, it's not the average rate of change anymore because there is no distance between the 2 points. So we actually refer to it as the instantaneous rate of change. So instantaneous rate of change. Okay, these two terms are pretty much interchangeable. All right, so make sure you have those written. Okay, now, how do we actually find the instantaneous rate of change? Well, what we're going to do is we're going to find the limit of the slope of the secant line as the points get closer and closer together. All right, now, we're going to write this limit using the points a comma f of a and a plus h comma f of a plus h. So I'm going to draw a curve here, and I'm going to exaggerate it. Here's a comma f of a. And then up here is going to be a plus h comma f of a plus h. All right. Now, there is a distance between these two. How far apart, horizontally speaking, are these 2 points? Well, if this one is at x equals a, and this one is at x equals a plus h, then the width between them is actually h, right? And so what we want to do is we want to find the slope of the secant line. So the secant line connecting these two, what would the slope of that secant line be? Well, it would be f of a plus h minus f of a divided by a plus h minus a. Now, that's the slope of the secant line. But we want these two to get infinitely close together, which means we want to calculate the limit as h approaches 0. So the limit as h approaches 0 is what is going to calculate the slope of the tangent line, or what we will refer to as the instantaneous rate of change. All right, and so we simplify this ever so slightly, and we write it as the limit as h approaches 0 of f of a plus h minus f of a all over, well, a minus a, that would just be h. Now, you probably should recall this, but it's very important that we understand that this is how we get the slope of the tangent line from the work that we did finding the slope of the secant line. All right. And so in practice, we're just going to do what we are used to from pre-calc. So in this example, it says find the instantaneous rate of change of f at x equals 5. And f of x is 3x minus 1. So what does that mean? That means find the limit as h approaches 0 of f of a plus h minus f of a over h. Now remember, in this case, a is 5, right? That's the specific value of x that we want to find the instantaneous rate of change. And so we're going to write it as f of a plus h. That'd be 3 times a plus h, in this case 5 plus h minus 1. So that's f of a plus h minus f of a, so that'd be 3 times 5 minus 1, all divided by h. Now, we want to carry out this limit. So obviously, we know that anytime we evaluate a limit, we need to plug in or substitute 0 in for h. But the way that this is set up, if you think about it, if you go back to here, the limit as h approaches 0, f of a plus h minus f of a over h, every time you set a problem up like this, it's always going to become 0 over 0. So we know that if we put 0 in for h here, we're going to get 0 over 0. So what does that mean? That means we need to simplify the numerator and reduce h. All right, so let's simplify the numerator. Limit as h approaches 0. All right, so I'm going to distribute the 3. So I get 15 plus 3h minus 1. And then I make sure I either simplify this or distribute the negative or whatever. So 3 times 5 is 15, minus 1 is 14. So I have minus 14 here, and then all divided by h. So I have 15 minus 1, 14, minus another 14, that's 0. So I'm left with the limit as h approaches 0 of 3h over h. So of course, h reduces, and I am left with the limit as h approaches 0 of just 3. So no place to plug 0 in because the h's are gone, so I end up with just 3. Sometimes the h's will disappear, other times the h's won't entirely disappear, and you'll have to put 0 in somewhere. But that means that the instantaneous rate of change of f at x equals 5 when f is 3x minus 1 is 3. Or you could also say that the slope of the tangent line to f of x equals 3x minus 1 is 3. Let's think about that. What is the slope of this line, 3x minus 1? Well, that is a line with a slope of 3. So clearly, at any point, it wouldn't have mattered if it was x equals 5 or 4 or 2 or negative 5. Any of those, we're asking, what is the slope of this curve or line? Well, of course, it's 3. So that gets us through slide number 41, and we will continue the notes in class.